Hello everyone, this is Ron Connor. So we're today looking at enums in Rust. I'm going over the Rust book to learn Rust myself, just showing you what I'm doing in these video series. All right, we'll look at enumerations, also referred to as enums. Enums allow you to define a type by enumerating its possible variants. Okay. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can be either something or nothing. And we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Okay, if let after that. All right, let's see. Defining an enum, where structs give you a way of grouping together related fields and data, like a rectangle. Let's say you have a rectangle struct, you can have width and height fields in it. Enums give you a way of saying a value is one of a possible set of values. So you could have something like this, struct, rectangle, and then width, let's say floating point number, and height, so F64. You could have a struct like this, right? A rectangle that has a width and a height. Whereas, let's see, you can have an enum. Rectangle is one of a set of possible shapes that also includes circle and triangle. To do this, Rust allows us to encode these possibilities as an enum. All right. Okay. So something like this, you could have struct triangle, and triangle would have a base and a height, maybe, and then a circle. And a circle would have a diameter, right? Or a radius, say a radius, F64. And then you could probably have an enum that's called shape that implements those. Say a rectangle, and then triangle, and a circle. Something like that. I think that's what they're talking about, at least. Here is an example enum. All right, let's look at a situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, two major standards are used for IP addresses, version 4 and version 6. Because these are the only possibilities for an IP address right now that our program will come across, we can enumerate all possible variants, which is where enumeration gets its name. So in your code, you could have only 3 possible shapes, and you can enumerate them, meaning have a shape enum and have all the variants listed here. And these variants are basically, they're structs. They're defined in your code as well. Any IP address can be either a version 4 or version 6 address, but not both at the same time. That property of IP addresses makes the enum data structure appropriate, because an enum value can only be one of its variants. Okay. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of IP address. Okay, yeah. We can express this concept in code by defining an IP address kind enumeration and listing the possible kinds an IP address can be, v4 and v6, like this. Okay. IP address kind is now a custom data type that we can use elsewhere in our code. Enum values. We can create instances of each of the 2 variants of IP address kind like this. Let for assignment IP address kind double colon v6. Okay. And then this 6 is another identifier of the type IP address kind of the variant v6. So v6 variant of the IP address kind enum. I wonder if there is a built-in function in Rust that tells you the type of an identifier. I haven't encountered that. Rust find type of an identifier. Okay, type ID. Globally unique identifier per type. An opaque object which does not allow inspection. Okay. Struct type ID. Okay, I don't know if this is it. Get type of variable. All right. Usually when people ask this question, they often want to emulate something like this. Right. Rust doesn't have this, as each variable has exactly one type known at compile time. And check like if x is a string in Rust would always boil down to if true or if false at compile time, so it would be pointless. But what people often might want instead is an enum. Enums can hold different types of data. They carry this information at runtime, so we can use match to inspect this information. Data string, x is string, what a string. They use match, which we haven't seen yet. We've used it in a previous chapter, video series, but I think we're going to see what matches later on. All right, I'm just going to wait until we get there. Okay, so let for IP address kind double colon v6. Note that the variants of the enum are namespaced under its identifier. So this is namespacing operator, I think. And we use a double colon to separate the two. This is useful because now both values, IP address kind v4 and IP address kind v6, are of the same type, IP address kind. We can then, for instance, define a function that takes any IP address kind, right? And we can call it with v4 or v6. Using enums has even more advantages. So here, like all of these structs become a shape type as well. Okay. So you could probably do something like, can I do shape rectangle? Right. And then rectangle, can I do, nope, not dot notation. What was it? How do I access width here? Anyway, I think I need to implement a constructor method, something, struct rectangle. Save line. I am very new in Rust. I do not know if I can do this. Rectangle. Let's get a new rectangle. Let's rect be a rectangle. And then, what is it saying? Oh, right. Struct literal syntax. Like this. Width 32, say 15, and then height 5. So rect is a rectangle. Okay. And how do I let rect enum, can I do this? Be a shape rectangle like this with 15 and height 25. These need to be no. Oh, it should be find value in this scope. Okay. Suffix F4 float valid suffixes are F32, F64. Oh, I see. That's how you do it. There we go. And what is this doing? Has no field name width. Variant shape rectangle. Okay, so this is not actually our rectangle. Struct. Expected value found struct. Struct literal. Okay. How about we do this? Get these in here. Okay, they don't like this either. Size found rectangle. Why? Why would you expect size? I do want to use a struct here. Can I do that? Nope. Okay, so how do I actually have a struct in an enum? Wonder. I can do this, right? No. Right. I need the debug symbol thingy. From the previous derived debug. Okay. What was it again? Derived debug. Okay. Number read. Here it is. What if I don't have it? Right. There is no struct. Now there is a struct. I have debug. Let's run this code. Cargo run. Rectangle with height. Okay, we got the rectangle information in the print line. That's good. And enum shape. I don't know how to actually what if I had like a square here? Would this be okay? Right, it is okay. So let's find out how to use struct with Rust. Enum, increment, quantity, something. Struct increment, quantity, decrement, quantity, and then a bunch of methods. Not what I'm looking for. Embed struct into enum. It's unnecessary. It's a struct like variant. Enums require pattern matching of some sort. See Rust by example here. Load, unload, key press, paste. Do they have structs with enums? Oh, there's no struct here. Generics. Nah, okay, I'll just forget about this for now. Oh, let's have a look. Okay, so there is an example here with a struct named IP address. Kind is IP address kind, blah, blah, blah. So you can have a rectangle here and you can have like kind here and call it shape. Okay. Shape is down there. Shape doesn't implement debug. Okay. Does it have to? There we go. What else? I don't have kind. Yeah. Using enums has even more advantage. Thinking more about the IP address type, at the moment we don't have a way to store the actual IP address data. We only know what kind it is. Given that you just learned about structs in chapter 5, you might be tempted to tackle this problem with structs. So struct IP address, kind IP, address kind, address string. Okay, yeah. Here we've defined a struct IP address that has two fields, a kind field that is of type IP address kind, and an address field type string. We have two instances of this struct. The first is home, and it has value IP address kind before, right? As its kind with associated address data of localhost. The second instance is loopback. It has the other variant, v6. We've used the struct to bundle the kind and address values together, so now the variant is associated with the value. However, representing the same concept using just an enum is more concise. So you don't need to combine structs with enums, basically. So here, I tried to do that, but failed. Rather than an enum inside a struct, we can put data directly into each enum variant. Like that. Okay, I see. So rectangle, you get F64, F64 as the width and height. The problem with that is it's not labeled, right? So yeah, I don't really like this over having explicit width and height keys like this. And triangle, you'd have base and height, circle with a radius. Yeah, I don't really like this. Can I use key value pairs with enums? Can put data directly into each enum variant. This new definition of the IP address enum says that both v4 and v6 variants will have associated string values. v4 has a string, which is the address, right? And v6 is also an address, which is the local host. We attach data to each variant of the enum directly, so there's no need for an extra struct. Here, it's also easier to see another detail of how enums work. The name of each enum variant that we define also becomes a function that constructs an instance of the enum. Right. Okay, yeah. That's what happens here. That is, IP address v4 is a function call that takes a string argument and returns an instance of the IP address type. We automatically get this constructor function defined as a result of defining the enum. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Right, okay. Version 4 IP addresses will always have 4 numeric components. Can I do something like this? What if I pass a rectangle struct here? What are you doing? What is this? Recursive type. Why? Right. Remove the kind shape. What about now? Okay, so we can do that. All right, so this is how you do it. Yes. Triangle takes a triangle type, and circle takes a circle struct type. Now let's get derived debugs on each of them so that the linter stops complaining. I think this is how it's done. So if I want to use the enum for this, I would have to do something like shape rectangle. And then inside here, what? Expected rectangle found that. Right, shape rectangle, and here you need to have a rectangle with the width of 15 f64 and height 25 f64. So that's how you do it. If you want to do it this way. Shape rectangle, taking a rectangle struct. If I want labels on my width and height. Man, don't like this syntax. Anyway. Okay. We've shown several ways to define data structures to store version 4 and version 6 IP addresses. Right, so here you can have the unsigned integer 8-bit for each of these. You don't need to have a string. In v6 you could have a string. Doesn't matter. And we did the same here. We use different types. Each of these are structs, so each of them is a type. So, however, as it turns out, wanting to store IP addresses and encode which kind they're so common that the standard library has a definition we can use. Let's look at how the standard library defines IP address. It has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of 2 different structs, which are defined differently for each variant. So these are the structs, right? This is the same, I guess, logic here. This code illustrates that you can put any kind of data inside an enum variant, strings, numeric types, or structs, for example. You can even include another enum. Also, standard library types are not are often not much more complicated than what you might come up with. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict, because we haven't brought the standard library's definition into our scope. Talk more about bringing types into scope in chapter 7. Let's look at another example of an enum in listing 6-2. This one has a wide variety of types embedded in its variants. Okay, yeah. This looks like a struct, and that is a string. Oh, look at that. You can do this. So I could do, why wasn't I able to do that then? I could do width, f64, and then height, 64, right? I could just do this, if this is possible. Yeah, so I don't need to actually define these structs outside. Okay, so if this is possible, this is much better. Triangle, let's say a base, a height, and a circle just has a radius. But still, let's name it. Have it named radius f64. There we go. Okay, this is much better than the previous example. Shape rectangle with height, triangle, base height, circle radius. This is much better. Syntax. And I'm glad that Rust actually allows this. Yeah, there we go. And let's run this. Shape has a derived implementation for the trait debug, but this is intentionally ignored during dead code analysis. Rectangle with awesome. This is awesome. Okay. Right, string, change color, other things. This enum has 4 variants with different types. Quit has no data associated with it at all. Move has name fields like a struct does. Exactly. So there's no need to define any struct outside, which is awesome. Never read. Really? Okay. Write includes a single string. Change color includes 3 I32 values. So it's like a tuple. It's just a string. This looks like a struct. Nice. Defining an enum with variants, such as the ones in listing 6-2, is similar to defining different kinds of struct definitions, except the enum doesn't use the struct keyword, and all the variants are grouped together under the message type. Right, exactly. The following structs could hold the same data that the preceding enum variants hold. Greet message, unit struct, move message. Right. But if we used the different structs, each of which has its own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6-2. Right, so I can write a function that takes, I don't know, a delete shape function that takes a shape, or the address of shape. Say shape, address of shape, and does something with it. Okay. IMPL message. So here, this could be a shape method as well. IMPL shape this, and then function del delete, and then takes the address of self. Does stuff. Delete, move, etc. Whatever. The body of the method would use self to get the value that we called the method on. This example, we've created a variable m that has the value that. Okay. And that is what self will be in the body of the call method when mcall runs. Right. Let's look at another enum in the standard library that is very common and useful, option. The option enum and its advantages over null values. This section explores a case study of option, which is another enum defined by the standard library. The option type includes the very common scenario in which a value could be something or it could be nothing. For example, if you request the first item in a non-empty list, you would get a value. If you request the first item in an empty list, you would get nothing. Expressing this concept in terms of the type system means that the compiler can check whether you've handled all the cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. Rust doesn't have the null feature that many other languages have. Null is a value that means there is no value there. In languages with null, variables can always be in one of two states, null or not null. In his 2009 presentation, Null References, the $1 Billion Mistake, Tony Hoare, I think it's Hoare, or Hoare, however it's pronounced, the inventor of null has to say, I call it my $1 billion mistake. At that time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. The problem with null values is that if you try to use a null value as a not null value, you'll get an error of some kind. Because this null or not null property is pervasive, it's extremely easy to make this kind of error. However, the concept that null is trying to express is still a useful one. And null is a value that is currently invalid or absent for some reason. The problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of a value being present or an absent. This enum is option T, and it is defined by the standard library as follows. Enum option T, there are two variants. One is none, with no data, and one is some, of type T. The option T enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. Its variants are also included in the prelude. You can use some and none directly without the option : prefix. So you don't need to use the option namespace. The option T enum is still just a regular enum, and some T and none are still variants of type option T. The T syntax is a feature of Rust we haven't talked about yet. It's a generic type parameter. And we'll cover generics in more detail in chapter 10. For now, all you need to know is that T means that some variant of the option enum can hold one piece of data of any type, and that each concrete type that gets used in place of T makes the overall option T type a different type. Okay. So here are some examples of using option values to hold numbers, number types, and string types. That's some number, assignment, sum 5. Okay. Some char, some e. The type of some number is option I32. The type of some char is option char, which is a different type. Rust can infer these types because we've specified a value inside the sum variant. For absent number, this guy, Rust requires us to annotate the overall option type. Option I32, none. The compiler can't infer the type that the corresponding sum variant will hold by looking only at a none value. Okay. Here we tell Rust that we mean for absent number to be of type option I32. When we have a sum value, we know that the value is present and the value is held within the sum variant. When we have a none value, in some sense it means the same thing as null. We don't have a valid value, so why is having option T any better than having null? In short, because option T and T, where T can be any type, are different types. There are different types. The compiler won't let us use an option T value as if it were definitely a valid value. For example, this code won't compile because it's trying to add an I8 to an option I8. It's saying no implementation for I8 plus option I8 for the addition operator. Intense. Okay. In effect, this error message means that Rust doesn't understand how to add an I8 and an option I8 because there are different types. When we have a value of a type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option I8 or whatever type of value we're working with do we have to worry about possibly not having a value. And the compiler will make sure we handle that case before using the value. In other words, you have to convert an option T to a T before you can perform T operations with it. So you need to convert an option I8 to an actual I8, signed integer of 8 bits, in order to perform the addition here. Okay. Generally, this helps to catch one of the most common issues with null, assuming that something isn't null when it actually is. Eliminating the risk of incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option T. Then, when you use that value, you are required to explicitly handle the case that when the value is null. So you need to actually be able to tell if your value is ever at risk of being null, so that you use option T instead of just a T. Where would this be used? I wonder. I wish there was a concrete example here. Then when you use that value, you are required to explicitly handle the case when the value is null. Everywhere that a value has a type that isn't an option T, you can safely assume that the value isn't null. This was a deliberate design decision for Rust to limit null's pervasiveness and increase the safety of Rust code. So how do you get the t value out of a sum variant when you have a value of type option t so that you can use that value? The option t enum has a large number of methods that are useful in a variety of situations. You can check them out in its documentation. Becoming familiar with the methods on option t will be extremely useful in your journey with Rust. In general, in order to use an option t value, you want to have code that will handle each variant. You want some code that will run only when you have some t value. This code is allowed to use the inner t. You want some other code to run only if you have a none value, and that code doesn't have t value available. The match expression is a control flow construct that does just this when used with enums. It will run different code depending on which variant of the enum it has, and that code can use the data inside the matching value. Okay, so we're gonna see match, the match control flow in the next chapter. Let's have a look at the documentation of option here. There is sum and something, is none, right? So if x is none, returns false. If x is indeed none, returns true. As ref, what is that? Converts from option t, or address of option t, to option address of t. I can't fathom where that would be useful. Still can print text. First cast with sref and consume that with map, leaving text on the stack. We haven't seen map yet, so I don't know what that means. Converts from address of mute option t to option address of mute t. Basically the same as above, but immutable. Variable as pin ref, converts from pin, whatever that means, as slice, returns a slice of the contained value, if any. If this is none, an empty slice is returned. This can be useful to have a single type of iterator over an option or a slice. Should you have an option address of t and wish to get a slice of t, you can unpack it via opt map or that. Okay, sure. As mute slice. Expect. We've used this one. Returns to contain some value, consuming the self value. Panics if the value is a none, with a custom panic message provided by message. Right. We've used this in one of the chapter 2, I think. See. Was it here? Go down. Match. We've used match, but where's the expect thing? Let me see. Expect. Right there. We need to use expect somewhere. Unwrap returns to contain some value, consuming the self value. Because this function may panic, its use is generally discouraged. Instead, prefer to use pattern matching and handle the none case explicitly, or call unwrap or else, unwrap or default pattern matching. Okay. So these are unsafe. Map. Maps an option T to option. What is U? Huh. What is U? We don't even know what U is. Okay, so I'll see you guys in the next video, which is going to be about match. Right here, the match control flow construct.